Hi, my name is Xiaowei, and I'm a postdoc researcher at the University of Virginia and the Cosmic AI Institute. I'd like to tell you today about my research on mapping dark matter with stars and AI today. What is dark matter? So it is a substance with weak and perhaps no interaction with normal matter, besides through gravity. We just call it dark matter because it does not emit or absorb light. And yet, dark matter makes up so much of the matter budget in the universe that it is the dominant source of gravity. As a result, it serves as the scaffolding for galaxy formation and shapes galaxies like our own Milky Way. Yet so far, we still have almost no clue about its nature. What type of particle could it be, if it is a particle at all, and how did it form in the first place in the universe? These are questions that require us to first know where dark matter is in the universe, as different theories of dark matter can predict subtly different structures of dark matter inside galaxies. But measuring these structures is very difficult, especially for distant galaxies where we may only have some images that look like these. So the research question I want to ask is, can we map something we cannot see using the things that we can see? In galaxies, what we see most directly are stars. Stars give us light. They trace part of the galaxy's structure, for example, where the dense center is, where the outskirts fade away, where the galaxy is smooth, clumpy, stretched, or disturbed. Underneath that visible structure is a much larger dark matter halo, which controls how the galaxy form and evolve. My project asks whether machine learning can help us bridge these two properties together. To do that, we need to train the machine learning model on simulated galaxies, for example, the DREAM simulation suite, where we know both sides of the story. In a simulation, we can see the stars, and we can also directly track the dark matter. So we give the model many examples. Here is a map of stars, and here is the corresponding map of the dark matter. Now, over time, the model learns the statistical relationship between the visible galaxy and the invisible mass around it. Then, once trained, we can give the model a new stellar map and ask what dark matter structure is most likely hiding underneath. I like to think of this as like kind of a cosmic translation problem. The model is not simply making up a picture, it is learning how to translate from one physical tracer, starlight, into another physical property, in this case dark matter, based on all these examples it has seen in the simulations. And the answer to that question, and our result, is that the model can indeed recover the broad dark matter structure of simulated galaxies from their stellar distribution, as you can see here. It can reproduce the overall shape of the dark matter halo, and it can also give us a way to estimate uncertainty, where the prediction is reliable and where the model is less sure. The broad goal here is not to replace the traditional astrophysical measurement for mapping out dark matter, but it's to build a new tool, because there are all these upcoming survey images that are going to give us billions of galaxies, and methods like this could help us very efficiently turn galaxy light into statistical maps of the unseen matter that shapes the universe. In other words, we may never photograph dark matter directly, but with the right combination of simulation, observation, and machine learning tools, we can begin to reconstruct the shadow of dark matter.